In the high-stakes domain of industrial aviation beyond the visual line of sight, or BVLOS, time is the critical asset. 4 years, engineers deploying autonomous systems for oil and gas inspection or regional 5G telecommunications coverage have hit a physical wall. We call it the LiPo Wall. Lithium polymer battery chemistry, at its very best, possesses a specific energy density of roughly 250 watt-hours per kilogram. For a 12-hour infrastructure security mission, the required battery mass is geometrically impossible for a vertical takeoff aircraft to lift. But here lies the brutal paradox of physical energy storage. The legacy fuel stack, Jet A1, diesel, or even standard 92-octane gasoline, possesses an extraordinary specific energy density of nearly 12,000 watt-hours per kilogram. In the pure mathematics of potential energy, fuel beats batteries by a factor of nearly 50 to 1. This paradox has forced systems engineers to execute a radical hardware retrofit. To unlock endurance that extends beyond hours and into days, they are turning autonomous VTOL aircraft into flying power plants. They are implementing heavy fuel and gas-electric hybrid architectures. This technology enables heavy industrial sensors, Skydio-class communication relays, and LTE range extenders to operate with unprecedented duration, fundamentally securing the remote frontiers of modern network infrastructure. Sending 800 volts up a tether solves the weight problem, but it limits mobility to a radius of 150 meters. To achieve true untethered, regional-scale endurance, the hybrid architecture performs a sophisticated energy transformation entirely on board the aircraft. It is crucial to understand that in a gas-electric series hybrid, the internal combustion engine is not directly connected to the propellers. It does not rotate the main vertical takeoff motors or the rear cruise propeller. Instead, the engine operates as a continuous-duty range extender and an airborne electrical generator. The system deconstruction is precise. Liquid heavy fuel is injected via a high-pressure electronic fuel injection system into the cylinder of a compact, high-RPM internal combustion engine. The engine's crankshaft is directly coupled to the rotor of a high-efficiency permanent magnet synchronous generator. The generator produces raw, unstable high-voltage alternating current. This AC stream flows immediately into a sophisticated, aerospace-grade power management unit, or PMU. The PMU rectifies and stabilizes this energy into a primary high-voltage direct current power bus, typically between 400 and 800 volts DC. This stabilized direct current becomes the lifeblood of the entire ecosystem, concurrently charging the onboard buffer batteries, powering the critical Skydio avionics and sensors, and delivering unlimited energy to the electronic speed controllers of the propulsion motors. While the hybrid generator solves the long-term endurance problem, it introduces a severe dynamic challenge: balancing instantaneous peak loads. A vertical takeoff aircraft running high-power Skydio relays requires immense energy spikes during takeoff, climbing, and hovering in strong maritime winds. The internal combustion engine is a mechanical system with sluggish response times. It cannot instantly throttle from 5 kilowatts to 25 kilowatts when the wind suddenly gusts. This is where the high C-rate buffer battery stack becomes the mission-critical component. It does not store hours of energy. It stores minutes of peak power. When the autopilot executes a violent maneuver or initiates the VTOL vertical landing sequence over a remote cellular Skydio site, the generator continues to run at its optimized, highly efficient constant RPM. But the power management unit instantaneously draws the remaining 15 kilowatts of required power from the high-discharge buffer battery. The battery provides the necessary torque and stability, while the generator works continuously to refill the battery whenever the system has spare capacity. From a thermal management perspective, this architecture is incredibly volatile. Converting mechanical energy to high-voltage AC and then to high-voltage DC has severe efficiency losses. That equals nearly 500 watts of pure waste heat generated inside a tightly sealed carbon fiber chassis. Catastrophic thermal shutdown of the transistors in the PMU, or generator winding insulation failure, can occur in seconds. The mechanical structure of the hybrid drone is therefore engineered around prop-wash thermal integration. The power management unit and the generator heatsinks are positioned directly within the high-velocity, turbulent airstream generated by the main vertical propellers. This ensures that even in static hover, when there is zero forward airspeed, hundreds of liters of cool air are forced through the cooling channels every second, keeping the internal flying power plant at a stable, efficient thermal equilibrium. Transforming a complex mechanical power plant for an aerospace environment requires relentless hardening against vibrations and atmospheric variables. A standard two-stroke engine is designed for constant air density at sea level. If the drone ascends to 3,000 meters during a remote perimeter patrol over a high-stakes 5G telecommunications installation, the air becomes thin and the air-fuel ratio collapses. The system relies entirely on an advanced electronic fuel injection, or EFI, computer. The onboard avionics suite continuously feeds barometric pressure, manifold temperature, and throttle position data to the EFI stack. The EFI adjusts the fuel injector duty cycle with surgical precision, ensuring that the heavy-fuel hybrid powertrain operates with optimal combustion efficiency regardless of altitude or environmental humidity. Furthermore, a mechanical engine running at 9,000 RPM generates immense harmonic vibrations. If left dampened, these vibrations will cause immediate mechanical fatigue in structural carbon fiber brackets and destroy the sensitive gyroscopes inside the critical skidio communication relays and stabilization gimbals. Aerospace engineers master these mechanics by integrating high-precision, viscoelastic harmonic dampening mounts. They isolate the engine from the airframe, absorbing the destructive energy waves before they reach the sensitive mission payloads. By mastering the strict physical interplay between high-voltage electrical conversion, internal combustion acoustics, electronic fuel injection, and dynamic thermal integration, systems engineers have created an untethered flying power grid. They have rewritten the rules of industrial automation, providing unparalleled, reliable autonomous duration that hardens the network infrastructure and secures the industrial frontiers of the modern world. Thank you for watching this technical breakdown on BlackBox UAV. Stay analytical, verify your telemetry parameters, and we will see you inside the next BlackBox session.